Bismillah, Alhamdulillah, Salatu Wassalamu ala Rasulillah. This is section 4.4, sorry, 4.3. What derivatives tell us about the shape of a graph? So, from the derivative, we can get some information about the shape of the graph. Let us find out. First, increasing or decreasing. If the first derivative is positive on an interval, then the function f is increasing on that interval. So if you look to this function, now from a to b, f is increasing. Now what about f prime? F prime is the first derivative. So it's the slope of the tangent line. If you take this point, the slope of the tangent line here, is it positive or negative? Since the tangent line is increasing, then its slope is positive. So if you choose any point here and draw the tangent line, you will find that the tangent line always increasing. So the derivative is always positive. So we get from here that when f prime is positive, the function is increasing. Similarly, from B to C, if you take any point and sketch the tangent line would be always decreasing. So the slope is negative. So f prime is negative. So we conclude from here what we call the increasing decreasing test. To find out whether the function is increasing or decreasing, just find f prime and study the signs of f prime. On the intervals in which f prime is positive, the function would be increasing. On the intervals on which f prime is negative, the function would be decreasing. So the graph of f prime of a function is shown. On what intervals f is increasing or decreasing? Okay, notice that this is the graph of f prime, not the graph of f. So we need to know some information about f from the graph of f prime. Well, f is increasing when f is increasing when f prime is positive, when f prime is greater than 0. This is the graph of f prime. The graph on the intervals in which the graph is above the x-axis, the graph is positive or y is positive. So from 0 to 1, from 0 to 1, the graph is above the x-axis. So f prime is positive. So f is increasing. From 3 to 5, the graph is also above the x-axis, and it's the graph of f prime. So f prime is positive, so f is increasing. So these are the intervals on which f is increasing. F would be decreasing where f prime is negative. And f prime, this is the graph of f prime. F prime is negative when the graph is below the x-axis. So from 1 to 3, f prime is negative, so f is decreasing. And from 5 to 6, f prime is negative, so f is decreasing. So this is the answer of part A. Part B, at what values of x does f have a local maximum or local minimum? Well, if will have local maximum or local minimum here, look here. What about B? B is a local maximum. C here is a local minimum. What happens? Why B is a local maximum? Because the function was increasing and then decreasing. So whenever the function is increasing, then decreasing, then we will have a local maximum. While if the function is decreasing, then increasing, we will have a local minimum. So let us discuss at 1 what happens. At 1, the function was increasing, and then from 1 to 3 it is decreasing. So the function was increasing, then decreasing. So at 1 we have a local maximum. So local maximum at what values of x? Local maximum at x equals 1. This is the answer of part B. So at 1 we will have a local maximum. Notice that f prime is 0 at 1. So whenever f prime is 0, in fact, we will have a local maximum or local minimum. So at 3, let us discuss at 3 what happens. At 3, f prime negative, and then it becomes positive. So it's decreasing, it was decreasing, and then f was decreasing, from 1 to 3 decreasing, and from 3 to 5 increasing. So at 3, there is a local minimum. So local minimum at x equals to 3. Now what about 5? F prime positive, then f prime negative. F prime, f increasing, then f decreasing, increasing, then decreasing. So it's the local maximum. So we have local maximum at x equals 1, 5, 1 and 5, and local minimum when x is equal to 3. Find where the function f is increasing and where it is decreasing. To answer the question, I need to find f prime. F prime is 12x to the power 3 minus 12x squared minus 24x. After finding f prime, I need to study the signs of f prime, where f prime is positive and where f prime is negative. And to study the signs of any quantity, I need to find the zeros of this quantity. After we find the zeros, now the quantity changes its signs are around the zeros. So I need the zeros of f prime. What are the zeros of f prime? So I put it equal to 0 and I solve it. Now I can divide now by 12, and I can take x as a common factor. So I will have x squared minus x, because I'm taking x as a common factor, and 24 divided by 12 is 2, and x finished. Now if you multiply, you have x cubed minus x squared minus 2x. And if you multiply by 12, you go back to the original equation. Now I can factor the second degree polynomial. I have x, and this one I can write it x minus 2 times x plus 1. So negative 2x plus is negative x. So this is the factored form. So I understand from here that the zeros of f prime are 0, 2, and negative 1. Either x is 0, you get 0, or x minus 2 is 0, so x is 2, or x plus 1 is 0, so x is negative 1. So these are the zeros. Now once you have the zeros of f prime, you can put these zeros on the number line. So this is negative infinity, this is infinity, the smallest is negative 1, then 0, then 2. So this is the number line, so make sure you put the zeros in order. And now I'll make this table. I'll study the signs of f prime, and then I will talk about f. Once I know that f prime is positive, then f would be increasing. If f prime is negative, then f would be decreasing. So to study the signs of f prime, this is f prime. Now, how many intervals do we have? 1, 2, 3, 4. We have 4 intervals. In each interval now, f prime is either positive or negative. So you know here in this graph, what are the zeros of f prime? 1, 3, 5. From 0 to 1, it's positive, f prime. From 1 to 3, f prime is negative. From 3 to 5, f prime is positive. From 5 to 6, it's negative. You see? So between the zeros, there will be one sign of f prime, either positive or negative. So for example, if I select a number greater than 2, 3 for example, so either you put 3 here, you replace 3, 12, 3 to the power 3 minus 12 times 9 minus 24 times 3 and find the sign, or I have an easy way. Look carefully. Actually, when I put equals to 0, I divide it by 12. Dividing by 12 will not change the sign of f prime. So I can use this quantity. This quantity have the same signs as f prime because f prime is just 12 times this. So if I replace x by 3 here, I can see that 3 is positive, 3 minus 2 is positive, 3 plus 1 is positive. If I multiply positive times positive times positive, it would be positive. So actually f prime to the right of 2 is positive. And look to something else. I have how many zeros of f prime? 3 zeros. And f prime has degree 3. Any degree 3 polynomial will have at maximum have negative plus negative. Because a zero of multiplicity 1, the function changes the sign around that zero. So since 2 is a zero of multiplicity 1, and we checked that it is positive to the right of 2, then f prime has to be negative to the left of 2. And now 0 is 0 of multiplicity 1, to the right of 0 negative, so to the left of 0 has to be positive. Negative 1 is a 0 of multiplicity 2, positive to the right, so negative should be to the left. And you know that from the difference between x and x squared. So y equals x now has a 0, and this 0 is a 0 of multiplicity 1. So to the left of 0, the function is negative, and the function is positive to the right. So the function changes the sign around this 0 because it's of multiplicity 1, or 3 or 5 odd multiplicities. For example, degree 3 is also like this. And the function changes the sign because the 0 is a 0 of multiplicity 3. While if you consider a 0 of multiplicity 2, now how many zeros are there for this function? 1 0. And this 0 has multiplicity 2. Look to the graph. The function is positive to the left of the 0 and positive to the right of the 0. So the function does not change the sign around zeros of multiplicity 2. That's a very important point. It will help you here. And instead of taking number in each interval and substituting in f prime, this may immediately save your time. So here f would be decreasing, here f is increasing, here f is decreasing, and here f is increasing. What is the question? Find where the function is increasing or decreasing. So I can say that f is increasing on the intervals from -1 to 0, union from 2 to infinity. And f is decreasing which intervals from -infinity to -1, union from 0 to 2. So that's the answer. Another question, suppose the derivative of a function is given by this. So you have the derivative is given. On what intervals f is increasing? Well, he is asking about increasing. Well, f would be increasing if f prime is positive. So this is f prime. Let us check where f prime is positive. Now look carefully. What are the zeros of f prime? 4 is a 0, and it's the 0 of multiplicity 2. So does not change the sign about 4. Actually, x minus 4 to the power 2, something always positive because it's degree 2. So if you replace x by any number, raise it to the power 2, it would be always positive. Also here, x minus 5, the 0 is 5, and it's the 0 of multiplicity 8. So the sign does not change around 5. And this is to the power 8, so this is always positive. So what is controlling the sign of f prime actually is this one, x plus 3 to the power 7. If this term is positive, f prime would be positive. If this term is negative, f prime would be negative. And this term, or x plus 3 to the power 7, if I ask you what is the 0 of x plus 3 to the power 7, the 0 is negative 3. You solve it. Okay, you can solve it. You take x plus 3 to the power 7 equals to 0. Of course, this means that what is inside is 0 because 0 to the power 7 is 0, nothing else, no other numbers. So whenever you have x plus 3 to the power n is 0, this means x plus 3 has to be 0. So x is negative 3. So the 0 is negative 3. Now, to the right of negative 3, what happens? Okay, so we can make a table only for negative 3 because negative 3 really controls the signs of f prime. Okay, so if you choose a number greater than negative 3, for example 0, 0 plus 3 positive, so f prime would be positive here. If you choose negative 4 or negative 5, this would be negative. You raise it to the power 7, it would stay negative. So f here is decreasing and f here is increasing, and he is asking on what intervals is f increasing. So the answer is from negative 3 to infinity, this function is increasing. So that's the answer of this question. Now let us talk about the first derivative test. This test is a test for local maximum and local minimum values. So suppose that C is a critical number. You remember the definition of the critical number in the previous section. Critical number is a number in the domain, and when f prime is 0 or f prime does not exist, of a continuous function f. So f is continuous and C is a critical number to f. If f prime changes from positive to negative at C, this means what? This means f changing from increasing to decreasing, then at C we have a local maximum. If f prime changes from negative to positive, this means what? F changes from decreasing to increasing, we will have a local minimum at C. If f prime does not change the sign, positive to the left, positive to the right, negative to the left, or negative to the right, then f has no local maximum or minimum at C. So a critical number could be local maximum, local minimum, or just nothing. It could have, of course, it have a horizontal tangent because f prime is 0, or f prime does not exist. So horizontal tangent or maybe vertical tangent. So here, f prime positive, f prime negative, we have a local maximum. F prime negative, f prime positive, we have a local minimum. F prime positive, F prime positive, to the left and to the right, no maximum, no minimum. Here also the same. So this is what we mean by first derivative test. It's a test to determine the critical numbers. Are they local maximum, local minimum, or nothing? Example, find the local minimum and maximum values of the function f in example 1. Okay, this is example 1. What do you see? F here decreasing, increasing. So at negative 1, what do we have? We have a local minimum. So we have a local minimum. The local minimum, find the local minimum. So the local minimum is f of negative 1. F of negative 1 is a local minimum, and f of 2 is also a local minimum. And you can find f of negative 1 by substituting -1 here in f. So to find f of -1, I use this definition. So 3 times -1 to the power 4 minus 4 times -1 to the power 3 minus 12 times -1 to the power 2 and plus 5. The answer is 0. So f of -1 and 0, sorry, f of -1, which is 0, is the local minimum. So this is the local minimum. And another local minimum is f of 2. And also you can find f of 2, 3 times 2 to the power 4 minus 4 times 2 to the power 3 minus 12 times 2 to the power 2 plus 5, -27. So f of 2, which is -27, is a local minimum. So we have two local minima for this function. Well, the local maximum is f of what? F changes from increasing to decreasing at 0. F of 0, and f of 0 is easy. It is just 5 if you replace x by 0. So f of 0 equals to 5 is a local maximum. So 5 is local maximum for f, the function f. Find the intervals on which f is increasing or decreasing, and find the local maximum and minimum values of f. So to find the intervals of increasing and decreasing and local maximum and minimum, we need to find the derivative f prime. F prime is 6x squared minus 30x plus 24. Now I need to put f prime equals to 0. I can take 6 as a common factor. So I have x squared minus 5x plus 4 equals to 0. I can divide by 6 and factor. So either x is 4 or x is 1. Now these are the zeros of f prime, 1 and 4. I put these zeros on the number line. So this is 1, this is 4, negative infinity, infinity. And I check the signs of f prime in these three intervals. Well, this is f prime. And if you notice, I did not do anything to f prime. I took 6 as a common factor. I divided by 6. So actually, this has the same sign as f prime. Now, this is degree 2. F prime is of degree 2. So here, one help, also another help for finding the signs quickly. Whenever you have degree 2, between the two zeros, between 1 and 4, the sign is opposite to the sign of x squared. X squared here is positive, 6x squared. So the sign between 1 and 4 is negative. So these are the signs of f prime immediately. Or you can do like what I did in the previous example. Substitute with a number greater than 4. For example, 5. 5 minus 4, 5 minus 1, positive. So this we have positive here. And these two zeros are zeros of multiplicity 1. So immediately you have positive, negative, positive. So f is increasing here, decreasing here, increasing here. So now the answer. F is increasing on the intervals from negative infinity to 1, union from 4 to infinity. And f is decreasing on the interval from 1 to 4. And now local maximum. Well, I'll have a local maximum. What is the local maximum? F of 1 is the local maximum because I have increasing then decreasing. So f of 1 is a local maximum, and I can find f of 1 from here. Okay, f of 1 is 2 minus 15 plus 24 minus 5, and it is 6. So 6 is the local maximum, or f of 1. Well, I have a local minimum also, and the local minimum is f of 4. Okay, f of 4 here is the local minimum, and I can find f of 4, 2 times 4 to the power 3 minus 15 times 4 to the power 2 plus 24 times 4 minus 5, and it is negative 21. And you notice that the local maximum, of course, is greater than 6 is greater than, of course, the local minimum, which is negative 21. Although if the function has a lot of zeros, it could happen otherwise. So this is the answer of this question. Another question, same, we need to find f prime. F prime is 24x to the power 3 minus 3 times 16, this is 48x to the power 2. Now I put f prime equals to 0. I can take 24x squared as a common factor. So I will have x minus 48 over 24 is 2. So this is equals to 0. I can divide by 24 and I have x squared times x minus 2 is 0. If you multiply back, you get x cubed minus 2x squared. Okay, so times 24, you will get f prime. So what are the zeros of f prime? So zeros of f prime are 0 and 2. All right, x minus 2 is 0, then x is 2. Notice that 0 is a 0 of multiplicity 2. And notice that the signs of f prime exactly the signs of this quantity, x squared times x minus 2. So if you put the zeros here, 0 and 2, these are the zeros of f prime from negative infinity to infinity. And here is f prime, and here is f. Okay. Now, notice that x squared is always positive. So actually what is controlling the sign of f prime is x minus 2. To the right of 2, if you put 3, 4, it is positive. To the left of 2, f prime is negative. And notice now that 2 is a 0 of multiplicity when the sign changes around 2, while 0 is a 0 of multiplicity 2, so the sign does not change around 0. So f here is decreasing, while f here is increasing. And f is increasing on 2 to infinity, and f is decreasing on negative infinity to 0, union 0 to 2, or you can just say from negative infinity to 2. Now, at 0, I don't have anything because function decreasing, so no local maximum here and no local minimum. But at 2, I'll have a local minimum. So there will be a local minimum. What is the local minimum? It is f of 2. F of 2 is the local minimum, and I can find f of 2 from here. I replace x by 2, so 6 times 2 to the power 4 minus 16 times 2 to the power 3 plus 1, and it is negative 31. So negative 31 is the local minimum of this function. Another example, I need to find f prime. I have a rational here function. So to find f prime, I need to use the quotient rule. X minus 5 squared, derivative of the numerator times the denominator, derivative of the denominator, which is 1, times the numerator. And please do not forget parentheses here because I have two terms. So I have 2x squared minus 10x, 2 times 5, minus x squared, and minus times minus plus 24. Now f prime would be 2x squared minus x squared is x squared minus 10x plus 24 over x minus 5 to the power 2. Now if I try to factor the polynomial in the numerator, okay, try to factor this polynomial, you will not be able to. If you find the discriminant, you will find the discriminant 100 minus 4 times 24. The discriminant is b squared minus 4 times a times c. Well, it is not 100 times minus 4 times 24. That's 4. So you will be able to factor this uh, polynomial. It's easy to factor it actually. So when you find the discriminant, this will help you to know that if the discriminant is positive, you can factor it. You can factor it into 6. Well, two numbers, their product is 24, their sum is negative 10, just negative 4 and negative 6. So this is f prime written in simplest form. Factored. Everything is factored. So I can see from here that f prime is 0 when x is 6 and x is 4. So these are the zeros of f prime. I can see also that f prime does not exist when x is 5. But 5 is not in the domain of the function. So 5 is not a critical number. These two are critical numbers, 6 and 4. But now, what about 5? Will it affect the sign of f prime? Notice that we have x minus 5 to the power 2. So actually, the sign of f prime is not affected by 5 because it has power 2. So to the right of 5 and to the left of 5, I will have the same sign. So this is f prime. Let me put all of them 4, 5, and 6, and here negative infinity to infinity. If you want, you can put at 5 here a dashed line to remind yourself that it is not a number in the domain. Now check the signs of f prime. Well, you can do it quickly. Either you take a number greater than 6, for example 7. 7 minus 4 is positive, 7 minus 6 is positive, so it's positive here. And now 6 is a 0 of multiplicity 1, so it would be negative here. 5 is a 0 of multiplicity 2, so the sign will not change. 4 is a 0 of multiplicity 1, so the sign would be positive here. Okay, you can do it quickly like this, or you can take a number in each interval and find the sign of f prime, or you can say that x minus 5 to the power 2, so it doesn't affect, so x minus 6 times x minus 4, and this is degree 2. Between the zeros, the sign is opposite to x squared, so between 4 and 6, the sign is negative. Anyway, you can find the signs of f prime. F would be increasing here, decreasing here, decreasing here, and increasing here. So f is increasing on the intervals from negative infinity to 4, union from 6 to infinity. And f is decreasing on the intervals from 4 to 5, union from 5 to 6. And it's better to write it, it's actually correct to write it like this here. If you say from 4 to 6, f is not defined at 5. Okay, f is not defined at 5. So you have to say from 4 to 5, union from 5 to 6. Actually, at 5, the function has a vertical asymptote. Okay, so it could be decreasing like this from here and like this from here. But you cannot say from 4 to 6 decreasing. You have to say from 4 to 5, union from 5 to 6. And now what about the local maximum and the local minimum? We have a local maximum. What is the local maximum? It is f of 4. F of 4. And how do we find f of 4? We use the definition of f of x. So f of 4 would be 4 to the power 2 minus 24 over 4 minus 5. And the answer is 8. So actually f of 4 is 8 and 8 is the local maximum. We have a local minimum also, and the local minimum is f of 6. F of 5 we don't have anything. F of 6, 6 to the power 2 minus 24 over 6 minus 5, which is 1, is 12. So 12 is the local minimum. Notice here, local minimum is 12, local maximum is 8. That's no problem, okay? That's no problem because this is a local maximum. So in that interval, around 4, it is local maximum, but around 6, it is local minimum. Another uh, question, f of x equals x to the power 4 times e to the power negative x. Well, to find f prime, I'll use the product rule. The derivative of x to the power 4, the first function, times the derivative times the second function, plus the first function times the derivative of the second function. Well, the derivative of e to the power negative x is e to the power negative x times the derivative of negative x, which is negative 1. Now I need to rearrange f prime, okay? So I can take e to the power negative x as a common factor. Taking a common factor is very important. So I will have 4x cubed from the first term. And here I have negative x to the power 4. So not only e to the power negative x is the common factor. I can take e to the power negative x down, so it would be e to the power x. And from these two terms, I can take x cubed as a common factor. So I will have 4 minus x. All right, taking x cubed, 4 minus 3 is 1. So this is f prime. So f prime would be 0, where if x cubed minus 4x is 0, if the numerator is 0. So I shouldn't write it like this. X cubed times 4 minus x. So either x cubed is 0, which means x is 0, or 4 minus x is 0, which means x is 4. So 0 and 4, f prime would be 0 when x is 0 and 4. F prime does not exist if the denominator is 0, but the denominator cannot be 0. E to the power x cannot be 0 because the graph of e is always above the x-axis. So we have two critical numbers for this function, 0 and 4. Let us put them here on the number line. Let us study the signs of f prime. Well, notice that 0 is a 0 of multiplicity 3. So the sign changes around it, like multiplicity 1. It is not an even multiplicity. So if I choose number 5, for example, 4 minus 5 is negative, and 5 cube is positive. From 0 to 4, if I choose 1, or you can just say 4 is a 0 of multiplicity 1, so it would be positive here. 0 is a 0 of multiplicity 3, so it would be negative here, okay? Or you just choose negative 1, and this is negative, and this would be positive, so the sign would be negative. So f is decreasing here, increasing here, and decreasing here. So f is increasing on 0, 4, and f is decreasing on negative infinity to 0, union 4 to infinity. And we have a local minimum. Yes, it is f of 0. And we can find f of 0 by replacing x by 0. 0 times anything is 0. So f of 0 is 0, and that's the local minimum. And the local maximum is f of 4. Okay, f of 4. And f of 4 is 4 to the power 4. If you multiply 4 to the power 4 times e to the power negative 4, you will get a number approximately 4.7. Okay, it is actually 4 to the power 4 times e to the power 4, and approximately it is 4 to the point 7. So these are the local maximum and the local minimum, and this is the end of this part. I'll stop here and continue section 4.3 in another video. Uh, Thank you very much.